This is a recording for pre-calculus, and this is note 6.4, part 2, and it is finding vector components. And so I really, the bottom line is you're going to have to know something that we'll go over at the end, but I want to take some time to kind of derive this concept as we go. So this is finding vector components. If you remember that kind of boat problem, you've already seen where two vectors are added to get a resultant vector, and lots of things in physics and engineering give the reverse problem, and that's decomposing a vector into the sum of two vector components. And so that's what we want to be able to do, is we want to decompose a given vector into the sum of two vector components. And this is just kind of to think about this problem from before. This boat, the force F, which is this one that goes kind of perpendicular, to, or vertical is what I should have said, due to gravity pulls the boat down the ramp and against the ramp as we look at that. So if you think about these two vectors that are going kind of down the ramp and kind of against the ramp, those two vectors, excuse me, are orthogonal vectors. And, kind of our resultant vector is this force vector that we look at right there. But we want to say these two vectors, W1 and W2, are orthogonal. So vector W1 and vector W2 are orthogonal vectors. And in this situation, thinking about that parallelogram method and, maybe going this way and then this way, this force here is really the force vector is really W1 plus W2. And so that's what we want to kind of look at is bringing those into their components. And then this is just kind of stated over here. So the negative component of W1 represents the force needed to keep the boat from rolling down the ramp, whereas W2 represents the force that the tires must withstand against the ramp. And so then we're going to look at this picture, and the other one kind of went like this, and we were going W1 here, W2 there. This is our new picture that we're going to use. Here's going to be W1 going that way, W2 is going that way, and the U that's the sum of them is going to be going that way. So we're just going to, and there's an obtuse version, but we're just going to kind of go through this acute version as we kind of talk about things. So you do want to write the definition of vector components, and then we'll kind of look at that in a little more detail. So it says, let vector u and vector v be non-zero vectors such that vector u is equal to vector w1 plus vector w2, where vector w1 and vector w2 are orthogonal. So we know what that means. They're orthogonal. So that means this is a right angle, as is over there. And W1 is parallel to vector v, and it's parallel to vector v or a scalar multiple of vector v. So I don't know, it's a little hard to see, but vector v is kind of shown right there, and w1 is kind of shown all the way there. So those are scalar multiples of each other. So if I know one, I can kind of multiply by some scalar to get the other. Then the other thing is the vectors w1 and w2 are called the vector components of vector u. So they're the components because if we add W1 and W2, we get that u. And also, then this is a little kind of interesting. The vector W1 is the projection of vector U onto V and is denoted, and I'm going to kind of rewrite that right here. W1 is, oh, sorry, let me just do a little better job with that. So W1 is equal to the projection, so we write a PROJ, of U onto V. So it's V that kind of goes way down in there and is denoted by this. And W2 is U minus W1, and that should make sense because they add to be that, is vector U minus W1. Okay, and so now we want to kind of use this information and kind of develop something to be able to find the projection of U onto V as we go. So I'm going to just start and I'm going to use my space over here. I'm going to write some things kind of towards the middle, and on the very right, I'm going to kind of think about some things. So from the beginning here, we have that, and I'm going to start with that. So vector U is equal to vector W1 plus vector W2. And then we're going to remind ourselves that, and I'm going to use this kind of orange color, we're going to remind ourselves that W1 is either parallel to or a scalar multiple of V. So if this is V and this is W1, we can take, say that W1 is equal to V times some scalar C because their direction is the same. So I'm going to write myself a little note. I can say, I'm going to say, remember, W1 is equal to C times V. And then I'm going to replace this W1 with C times V. And I'm replacing it first, but then I'm just going to write this. So vector U is C times V plus W2. Now, just because we have a goal in mind to be able to figure out what this projection of U on V is, onto V is. So we're going to just now we're going to take the dot product of each side with V. So we're gonna take this dot V. Oh, I just wrote it as a U. This dot V, this side dot V, and this side dot V. And so we'll write this in parentheses now. So we're going to take U dot V, and that's equal to CV plus W2 dot V. So now we've got kind of a dot product in here that we'll be using. And then over here, if you remember, we can kind of distribute that dot product. And so I'm going to take, the CV dot V, and I'm going to take this dot V. So I'm just going to rewrite that. So I've got U dot V equals CV dot V plus W2 dot V as we go. And so then this one is V dot V, and do you remember that V dot V is the magnitude of V squared. So I'm going to use a different color here. And so I'm also going to remember, oh, that was very thick. I don't want it to be that way. We'll also remember that V dot V is equal to the magnitude of V squared. And so I'm going to replace that with the magnitude of V squared. And we'll just write all the rest. U dot V is equal to C times the magnitude of V squared plus W2 dot V. Now, look at the picture a minute, and that's over here, and look at W2 and V. What do you notice about the angle in between them? Do you notice, not this theta angle that's here, but if W2 is there and V goes out that way, didn't we just say a few minutes ago that that angle is a right angle? So that means that W2 and V are orthogonal, and so their dot product is 0. So, and that's, I'm getting right there with that. So W2 and V are orthogonal. So W2 dot V is going to equal 0. So I can put that in as 0, and I'll just do that right now. So I get U dot V equals C, and I'll just go back to this, the magnitude of V squared plus, and now that is 0. So then I'll just write it without the 0. So U dot V is equal to C times the magnitude of V squared. And now let's get C alone. So we want to know what that scalar C is as we look at this. And so to get that alone, we're just going to divide each side by the magnitude of V squared. So the magnitude of V squared. And so C, I'm going to flip those then and just say C is equal to the dot product U dot V over the magnitude of V squared. And you know, kind of think about that. Cosine of the angle was the dot product over the magnitude of one times the magnitude of the other. And so, you know, this isn't super far removed from that as we look at this. So now, W1, if you remember that W1 is several things. So W1 is the projection of U on V, and W1 is also C times V, kind of. I go, W1 was also C times V, and now we can replace that C with all of this, and so we can get a lot of relationships here. And so I'm going to write them right below here. I don't know if I can kind of see everything at the same time. Let me try. So we're going to say some concluding things. So vector W1 is equal to, and I'm first going to write it as that projection, the projection of U onto V, and it also is equal to C times vector V. And so it's also equal to C, we are going to replace with all that, U dot V over the magnitude of V squared, and then times vector V. So the real thing that we're going to get here is that this is equal to all of that. And so I am actually just going to write that right now. So the projection of U onto V is equal to the dot product of u dot v over the magnitude of v squared times vector v. And that's what we want to kind of remember or know as we go through this. So I have a couple slides here. I'll leave those kind of on this, and then we'll go to a problem. Here is that projection, but in my mind, if I just show you that right away, it's kind of maybe harder to follow in that regard. But if you want to pause this and write just that, go ahead. We've kind of developed that as we went. Okay, moving on. Here is problem number 5. So you might want to write some directions here. You want to find the projection of vector u, which is equal to 3, -5, onto vector v, which is 6, 2, and then write vector u as the sum of two orthogonal vectors, one of which is the projection of u onto v. And so I like to break this into two parts. I feel like part one or part A is to find this projection of u, projection of vector u onto vector v. Oh, well, actually, I'm going to write vector u, which is 3, -5, onto v, which is 6, 2. And then I'm just going to call it W1 because that's what we were using before. So W1 is the projection of U onto V. And so that is U dot V over the magnitude of V squared times vector V. And if you want to try that, go ahead and we'll see what you get. Otherwise, I'll just kind of work through that. I think I'll do it in real time just because it's a little involved. So U dot V is going to equal 3 times 6 plus -5 times 2, which is 18 minus 10, which is 8. The magnitude of V is the square root of 6 squared plus 2 squared, square root of 36 and 4, square root of 40, and so the magnitude of V squared is just plain 40. And I could have done that, just by using the dot product of V times itself, but that's okay. And so let's see what this gives us. We've got that dot product, 8 over 40, and we're going to multiply that times the vector 6, 2. And so 8 over 40 is 1/5 times that vector 6, 2. And so that is going to be 6/5, comma, 2/5. Oops, vector in component form. And that is two things. That is W1, and it is also the projection of U onto V. So that's kind of part one or part A of this whole thing. And then for part 2 or part B, I'm going to now do this, write U as the sum of two orthogonal vectors, one of which is this projection one. So I've already got this one. And so I'm going to write myself a directive. I'm going to write vector U as the sum of two orthogonal vectors, one of which is the projection of U onto V. And I'm just going to write equals W1 so that I just kind of know that. So now I'm going to say for this one, this vector U is going to be W1 plus W2. And it's W2 that I want to find. So if I subtract W1, that means W2 over right on the left is equal to U minus W1. And I happen to know both of those. So U is one of my original vectors, and W1 is this one that is right here. And so all I have to do is subtract those two vectors, and that should be my W2 vector, and then I'll write my answer. So W2 is U, which is 3, -5, minus the 6/5, comma, 2/5. And I'll just get a common denominator, so minus 6/5, comma, 2/5. 5 is my common denominator, so 3 is 15/5. -5 is -25/5. When I add things together, I get 15 and 6, which is, or excuse me, 15 minus 6, my apologies, which is 9/5. And -25/5 minus 2/5 is -27/5. So that is W2. And I had to write U as this sum. So that means that if I go kind of from there down here, that means vector U is equal to the 6/5 2/5, which is W1, plus this new one, which is 9/5, -27/5. And, you know, it says that we have to know that these are orthogonal. So we'll, as a final like part here, we'll check that W1 and W2 are orthogonal. And so why don't you do that? And we'll quit right there, and then on the next recording we'll pick that up by showing that those are orthogonal.